The idea of a machine truly seeing an image, that used to be pure science fiction. But then, over just the last decade or so, this incredible series of breakthroughs made it a reality. So today, we're going to trace that story. We're going to see how modern AI vision was built, literally one brilliant idea at a time.
Okay, so here's the plan. We're going to start with what you could call the Big Bang moment. That's AlexNet. Then we'll follow the breadcrumbs and see how researchers started building smarter, deeper networks. And we'll wrap up with how they eventually came up with these really elegant rules for designing them from the ground up. All right, so let's set the scene. Our story really kicks off in 2012. And believe me, this was the year that changed everything for computer vision. So you got to understand, before 2012, computer vision was this painstaking manual process. I mean, researchers would spend years handcrafting these complex algorithms just to detect things like edges and corners. The actual learning part, it was almost an afterthought. But after 2012, the whole paradigm just completely flipped on its head. Suddenly, instead of us telling the machine what to look for, the machine started learning the important features all on its own, directly from the pixels. Now, what's wild is that the core idea here, convolutional neural networks or CNNs, that wasn't new at all. I mean, a network called Linnet showed their potential way back in 1995. But then, for the next 15 years, nothing. The idea just kind of stalled out. It was seen as this interesting academic curiosity, but totally impractical for the real world. So, what finally changed? Well, it turns out it was a perfect storm, really. Two key ingredients were missing, and they both arrived at around the same time. First up, data. We're talking a massive amount of data. The ImageNet dataset dropped, and suddenly we had over 1 million high-res labeled images. That's an unprecedented amount of visual information for a machine to learn from. And second, the hardware finally caught up. All those GPUs that were being built for high-end gaming, turns out they were absolutely perfect for the kind of parallel number crunching you need to train these deep neural networks. So you've got the data, you've got the hardware, and then this network called AlexNet enters the annual ImageNet competition. And it didn't just win, it absolutely demolished the competition. I mean, the margin wasn't even close. And that was it. That was the undeniable proof. The deep learning era in computer vision had officially begun. Okay, so AlexNet basically kicked the door down. It opened the floodgates. But if we're being honest, its design was a little, clunky. The next big step was to get more systematic, to stop thinking about individual layers and start creating these reusable blocks, kind of like Lego bricks for building networks. And that's where the VGG network came in. It introduced this really elegant idea of a simple, repeatable block. You have a few convolution layers, an activation function, and then a pooling layer. That's it. And by just stacking these simple, identical units, you could suddenly build these incredibly deep and powerful networks in a really systematic way. But there was a catch. These early networks had this one massive Achilles heel. See, the final few layers of the network, the ones that actually make the final decision, they were gigantic, just absurdly inefficient. To put it in perspective, for AlexNet, those last few layers alone took up nearly a gigabyte of memory. That's a huge bottleneck. So how do you fix that? Well, the network and network architecture, we'll just call it NIN, came along with two really clever solutions. First, they use these tiny one-by-one convolutions. You can think of them like mini neural networks that run on every single pixel, letting the network learn much more complex features. And second, and this was the big one, it completely got rid of those giant final layers. Instead, it used something called global average pooling, which basically just averages out each feature app, a way more efficient approach. And the impact of this? It was huge. I mean, just look at the difference. You're swapping out this massive memory-hogging bottleneck for this super lean, efficient layer that uses a tiny fraction of the parameters. This is the innovation that really made truly deep, practical networks possible. All right, so now we have these new, smarter blocks. The path forward seems pretty obvious, right? Just stack them up, go deeper. But researchers very quickly ran into this really strange, totally counterintuitive problem. They called it the degradation problem. And here's what was so weird about it. A 50-layer network would often perform worse than a 20-layer one. Adding more layers was actually hurting performance. And that just made no sense at all. The solution came from a network called ResNet. And it was just brilliant in its simplicity. See, instead of forcing a block of layers to learn a whole transformation from scratch, they added what's called a shortcut connection. It basically just lets the original input bypass the block and get added back in at the end. So now the layers don't have to learn the whole thing, they only have to learn the difference, or the residual. And think about it. If a layer isn't really needed, it's way easier for it to learn to output 0, to do nothing, than it is to learn a perfect copy and paste of the import.
This simple idea, this little shortcut, it was an absolute game changer. Revolutionary. It just completely solved the degradation problem. Overnight. And it suddenly made it possible to train networks that were hundreds, even thousands of layers deep. Seriously, the residual connection is still one of the most fundamental, most important building blocks in all of deep learning today. Okay, so the depth problem is solved. What's next? Well, the next wave of innovation started to focus on making the connections within the blocks even smarter. The big question was, how can we reuse information even more effectively? So, ResNet added its input back to its output. But then a new architecture called DenseNet came along and asked a really interesting question. What if, instead of adding them, we just stacked them? What if we concatenated them? So in a DenseNet, every single layer gets the feature maps from all the layers that came before it, creating this incredibly dense web of connections. Now, this was super powerful. It encouraged a massive amount of feature reuse. But as you can probably guess, there was a big downside. These feature maps just kept growing and growing with each layer, which led to enormous memory usage. It's that classic trade-off, right? Performance versus resources. And that brings us to our final big evolutionary step. Because after years of painstakingly designing these individual, specific networks, researchers took a step back and started asking a much bigger question. Forget designing one network. Are there universal principles for what makes any network good? This was the idea behind the RegNet project. Instead of trying to find that one perfect needle in a haystack, they decided to just analyze the entire haystack. They literally tested thousands of randomly generated network architectures and just looked for the common patterns, the things that consistently led to good performance. And what they found was amazing. They distilled all of that complexity down to just a handful of simple, elegant rules for network design. For instance, they found that the best performing networks don't actually use some common tricks, like bottlenecks. Instead, they just have this very clean, predictable growth pattern. They get gradually deeper and gradually wider from start to finish. It was like they discovered a blueprint for building great networks without all the guesswork. So when you step back and look at it, it's incredible. In less than a decade, the field of AI vision went from a single chaotic breakthrough with AlexNet to this mature engineering discipline with clear, established design principles. But that leaves us with a really provocative thought. Just as we were finally writing the rulebook for how to build the perfect convolutional neural network, a completely different type of architecture, something called a transformer, which was born in the world of language processing, it just arrived on the scene and started breaking all the computer vision records. But the story of how and why that happened, well, that's a story for another explainer.